for a big company operating in the military field. So in a sense, I was doing the ultimate form of I/O. And then I landed into, when I landed the job as a Scala programmer, I moved to Manchester. But my real passion was to do Haskell. And I had the opportunity when, in October 2013, I was offered a position as a full-time Haskell developer in Brighton. That picture was actually taken the day of the interview. And here I'm working for Iris Connect. So who we are, Iris is essentially a CPD tool, where CPD is the acronym for Continuing Professional Development, and it empowers the teacher to record and share their lessons and best practices. At the moment, we are present in almost 2,000 schools worldwide, mostly UK and Europe. The tool itself is used by 32K teachers, and we have roughly 100 gigabytes of new content uploaded every day into the platform. So as you can imagine, this content is mainly videos, so it's an important asset for our business. And this is how Iris Connect appears to the final front-end customer, so in the sort of the shape of a web application. Those squares, little squares that you see there, is what we call reflections. So a reflection is such a collection of videos and is a self-contained unit of learning. And videos which can be uploaded into our platform using one of three different methods. You have the manual upload, which is exactly what you may think. So it allows to upload arbitrary video into the platform. Or you can use one of the two devices at the bottom. We have this live view, which is essentially a camera connected to the internet, which can then upload either to, say, a shared Samba drive or in an upload box, which is an optional piece of kit we sell, or the Discovery Kit, which is a tripod with a tracking and rotating device where you can mount any iOS-compatible device, and we ship an iPad mini as part of the kit, and of course, an iOS application as part of that. So in terms of our development stack and how it looks like, sorry, it's not behaving how it should. We have this recurring team of Greek gods nowadays, and we have, this every component in our architecture is named after a Greek god, which rapidly snowballed. I basically put in the different projects into different layers of, depending on how much interaction we have with the front-end customers. So the one at the bottom are one which sits behind the lines. We have Atlas, which is our sort of back-end server, and is essentially the initial effort was carried on by my colleague Chris Dornan with the help of Will Typed, which I want to publicly thank. And it's essentially what is informally referred as the version 2 of the platform. So we rewrote the platform from the initial version, which we call version 1, which was a monolithic Ruby on Rails application. And 2 years ago, we decided to rewrite this from scratch, using Haskell for the backend, but using more, in a sense, conservative choices for the front end. So this is why some of those boxes are white, because it's what is not Haskell. So what you see as a black dotted components is our Haskell software. All the rest is written mainly in iOS application. Of course, is self-descriptive. Athena, which is basically what you just saw in the previous slide, which is the web application, and the upload box are written in Ruby using Ruby on Rails. But as I said, Atlas is the big main component where all our business logic lives, and it exposes a library we sort of use as a foundation of the other projects. In the middle, we have the projects I personally built, which we have Chronos, which is a Snap web application. It's a full-stack web application using PureScript and Heist for the templating, and for the backend, just the plain Snap server. Hermes, which is the sort of the meat of the talk, and is the video transcoding server. So it's a cluster of machines which can take whatever videos the customer uploads and turn that into a streamable, something that the customer can actually play back. And the PAN is just a stats aggregator for the Hermes, so we can plot the AC2 cost over time or the efficiency, things like that. And finally, at the top, we have the customer-facing application, Athena, I just said to you, iOS application, and the newborn, which is Aphrodite, which is essentially a metrics dashboard for our Atlas data model. And although we initially started as this sort of two-split technology stack, after 2 years, our experience with Haskell has been so successful, both in terms of development and from a business point of view, then for Aphrodite, which is our latest project, we have decided to go with Haskell, just to give you a sort of feedback on how is our experience with Haskell. Unfortunately, my armband decided to die exactly the day it was meant. Whoa, what's going on. Okay. So this is Hermes. So let's talk a bit about Hermes. And there is a bit of a funny anecdote. So it was October 2013. I was just being hired, and we were sitting in a sunny Brighton having lunch outside with my colleague Chris. And Chris said, you know, I have a very interesting project for you. It's called Hermes. It's the media transcoding pipeline, and I would like you to, take over. I said, wow, cool. Let me check out the code. And the code was literally just 3 files. And 2 of them were, bash scripts. In all fairness, the only single file was calling back into a library Chris wrote to interface with ETS, which is the Amazon Elastic Transcoder. So it's a way of transcoding videos in the cloud. But after 2 years now, we are almost, hitting 13K lines of code, and we have, no bash inside apart from DevOps tidbits. Now it's behaving again. So in terms of Hermes challenges, when I came on board and I decided to take the lead on the project, the business was really clear on one of the main aspects in terms of requirements. So one of the frustrations of the version 1 of the platform is that they had this monolithical, beastly machine, very powerful Amazon machine, sitting there and just crunching videos as they came along. So it was, I think, like 32 core, something like that, which was really good in terms of turnaround time if you had like a very few jobs, so a very low traffic pattern. But during high traffic days, all this computational power was evenly spread across all these different jobs. So the customer experience was so-so. And also the cost line was a flat one, because this machine needed to be up and running 24 hours. So they wanted something really capable of scaling according to the traffic pattern and the power. And looking forward, it was really clear to see that we wanted something to be scalable, fault-tolerant, and distributed. And this immediately ring a bell, right? So, which is exactly what the cluster is about. So we wanted the cluster, and we wanted to create this cluster with Haskell. But at the same time, we have this tension. From one side, we have a cluster, which is typically a very stateful architecture, because machines need to know each other in order to communicate. Also videos, transcoding is another very stateful operation, because you need to sort of crunch bytes as you go along. But as good Haskell programmers, potentially, we would like to have our components as stateless as possible, and potentially treat videos as persistent data structures. So this is what I sort of embarked into, and I tried to aim. For the cluster itself, it was kind of easy, because in literature, this is what is called a shared nothing architecture. So I put a definition from Wikipedia, but it's just as good as many. It says that in a shared nothing architecture, each node is self-sufficient and there is no single point of contention, which is really good, because it means that if a node dies, I'm not sort of dependent from that node, but everyone is able to do the job as the one which died. So I went for that. And you're familiar with the popular quote from Butler Lampson that all problems in computer science can be solved by adding another level of indirection. So I started to add in my level of indirection, and I picked RabbitMQ. The reason for RabbitMQ was mainly historical. It was the technology I had the chance of interacting most at work. In my previous work, but in retrospect, it was just a brilliant choice. I mean, I cannot stress enough how pleased we are with RabbitMQ. We have been running it on a humble, medium AWS machine for almost 2 years now, and touching wood, there was no single time where we had to do some sort of maintenance or it sort of crashed unexpectedly. So it was really, really reliable. On top of that, it was really easy to set up. It can be configured to operate in a cluster and in a confederation of nodes. So if one node dies, you also get sort of your fault tolerance. It's extremely reliable, as I said, and there are really good Haskell bindings for it, and we even contributed a couple of patches upstream. But of course, generally arise a question, can I possibly move these blobs of data across the wire? It wouldn't be sort of feasible to do just to take the binary blob and move that, right? So we came up with this abstraction called the media key. Sorry if it perhaps is a bit tiny to see in the back, but it's just essentially a collection of tokens separated by hyphens. And I like to think about it like a sort of IP address for videos, and the reason will be possibly clear in a couple of slides. But in all fairness also, This, and all the credits goes to my colleague Chris Dornan for this lovely abstraction. And this was actually present in the very first iteration of the Atlas business model, but it was just in retrospective the perfect choice for the architecture I had in mind. So it seems almost like all the pieces went and fit together to form what we have. I won't go into too much detail on that because it's not very important for the rest of the talk. I will just concentrate on the last 3 tokens. So that vid that you see there, which is this called the channel type, is essentially serve the purpose of mapping a video intended as a RESTful sort of logical unit to one or more sort of physical videos. And this is because at Iris, we do not offer only the vanilla kind of video, but we also offer something called the dual view. So we give the possibility to record from 2 different upload sources and then sort of upload them together and stitch them together physically, one beside the other, to give, for example, the full view on the classroom and the teacher. And in this case, you have the sort of an impedance mismatch between your physical video, which you want to represent. You have 2 physical videos, right? The left part and the right part. But you still want to represent that as a single logical unit. And this is what we use the channel types for. So we have like a vid, which is a single video, so it's just a plain normal video. But that could also be like a VDL, which identifies the left part, or a VD right, or a VDC, which is the central stitched together video. Then we have the video products, which is essentially each lowercase letter identifies an output, so artifact, which essentially instruct Hermes how much output product we want from the input video from the customer. So in the example, we have 3. We have S, which is the sort of vanilla standard definition video, which the user can stream on the desktop. We have M, which is the HLS Apple streaming, adaptive streaming product for the mobile. And C is this what we call a cartoonized video. So of course, when working in school with children, privacy is something that you really need to think really careful. And we offer this sort of cartoonized, anonymized video, which essentially applies a video filter with a sort of cartoony video filter on top of the normal video, which gives you that level of anonymity without turning that in a sort of nasty, pixely video. So it works really well for us. And finally, the MAC is just a way to avoid submission of bogus keys and having the customers using the cluster for free. And before we crack on, this is the architecture, how I sort of told you. On the left part, we have the Atlas and the 3 different upload methods I told you about. Everyone basically pump media keys into this elastic load balancer, which is just a way for us to put multiple servers under a single DNS and do some round-robin dispatching. The servers themselves just do 2 things. They do some kind of pre-syncing, and also they forward the media key into the RabbitMQ. And RabbitMQ, at the very end, we have the workers. We just suck up media keys from the queues and does the proper video transcoding. And what is nice about this is that, of course, workers and servers, they share the same code. Basically, the server is just a sort of stripped-down worker without like a Boolean flag, which instructs them to pull stuff from the Rabbit. But also, they are completely stateless in the sense that there is only a local state, but the machines do not communicate with each other. So if one dies, I couldn't care less. Same applies for the servers. So it's a really nice architecture to deal with. So, but what about data storage? So I'm 20 minutes into the presentation, and you are probably still wondering, okay, but where are you physically storing the video? Good question. And it comes as no surprise that we are leveraging AWS quite massively. So we are using EC2 for our cloud computing needs, and we are using S3 for data storage. And this is why I told you that the media key for me is sort of like of IP address for videos. It's because that media key uniquely maps to a location on S3. So each media key that we spawn correspond, without risk of collision, to a unique location to S3, which is kind of neat. And also what we do when we receive the video from the customer, we store this video in a particular location, and this operation happens in the servers before we even push the things to the workers. We call this generation file, the generation 0 file, the master file. And such master file is immutable, which means that once we write it, we never touch it again, which puts us in a very good position with the customer, because we can say, okay, no matter how much we screw with the video transcoding, we can still take your original video and still reprocess it. And also because now, when we need to create a new product, like the standard definition or the cartoon, we do not modify the master file. We simply create a different output product into a different S3 bucket. So in a sense, we are treating videos as immutable data structures because we are not messing around with the original one, but we are creating like a copy in a different bucket. And exactly as concurrency and parallelism are really easy to do when you have persistent data structures, the same applies for our cluster. Because now I can split the video media key in, there are some API I can use in the Atlas library, which allows me to split video media key into multiple keys, which are just one product. And then I can submit this either to the same worker or just throw them into the RabbitMQ. And the workers, there will be no need for sort of locking or nesty interleaves because everything will completely work in a different buckets and it will just give me the peace of mind. So it really worked really well for us. Okay, but what about scalability? So the talk is called Scalable and Reliable Video Transcoding, but I didn't talk about scalability yet. Well, scalability, again, we sort of started with a naive, easy approach, and we use AWS for this. So AWS gives you something called the auto-scaling groups, which is essentially a way of creating a cluster. You can specify your base image you want to start with, sort of an upper bound and a lower bound in terms of machine that you want to spawn, and the sort of metrics that you can monitor. And if these metrics sort of trip some sort of alarm, you can trigger a scaling operation. And this scaling operation were, unsurprisingly, scaling up and scaling down, both sort of driven by the CPU percentage over time. So the sort of rationale was that if it was under high stress, we will spawn a new machine. If it were sort of very sort of low traffic and sort of low CPU consumption, we will sort of scale down. This kind of worked. I mean, it worked, but it had some sort of drawbacks. The scaling up was too conservative and slow because remember it will need like 15 minutes to do this for sort of initial round trip because you can specify the period you want your alarm to trip for be like an effective scale location to take up, and so this was too conservative. You will have like other jobs piling up in the queue, and you would possibly couldn't sort of match up with those. Also, scaling down suffers similar problems because it was too conservative. So at the end of the day, we still have like dozens of machine runnings, which still impacted our cost. So results was unoptimal for the customers and unoptimal for us in terms of cost. So we reviewed completely the scaling algorithm. And for the scaling up was kind of easy. And I'm sort of doing a bit of a digression on how RabbitMQ works, trying to oversimplify. So basically in Rabbit, a queue, a message can be in two possible states. It can be in what we call an unacknowledged state, which means that there is, at the other end, someone, like a worker, which is actively sort of processing this job. And what is neat about RabbitMQ is that if this worker dies in the middle of the computation and he didn't hack back the job, Rabbit is able to recognize this and put back the message on the queue in the second state, which is this ready state. So ready means essentially I'm waiting for a transcoding slot, right? So I'm waiting for a possibility to use the cluster. And you can modify the number of simultaneously unacknowledged jobs that each machine can have by a parameter called the prefetch count. So we put our prefetch count to 1 to avoid CPU trashing. So we effectively, everything which is not which is ready, it actually quite sort of correctly identifies the number of jobs waiting, and just customers impatiently waiting for their videos. So basically we monitor this ready figure and we spawn as many machines as that ready figure is, which allow us to scale really broadly and sort of instead of spawning one machine at a time, we spawn as many as the customer needs at that particular time. And thanks to the AWS sort of upper bound, we can keep cost at bay because we never go above the threshold. So that was kind of easy. The scaling down was more interesting because here we have two sort of attention. Again, from one side, we want to kill the machine as soon as possible, right? Because if we kill it, it means that we are not paying for it. Kind of, isn't very not true. At the same time, we would like to optimize the time it stays around, and it will be clear later on. But last but not least, the machine needs to die and commit suicide alone, which I know that it's sad. But at the same time, because it's a shared nothing architecture, so nobody needs to know the state of someone else. So everyone needs to take a local decision, which sort of complicated a bit things. And what we did, I mean, the abstraction I came up with, I know this is not a very particular, it's a bit of a grim name, is this Reaper thing, which is essentially a data structure which encapsulates a timeout, which can be, it's a maybe, so if it's a nothing, you are not enforcing a timeout at all. A bunch of I/O actions, one which is your reaping condition, and one is the reaping action itself. A bunch of essentially mutable variables which are needed to communicate back with the transcoders, which is, I will introduce them to you in a couple of slides. And the Poisson flask is sort of, is like the Poisson pill, but it's like a liquid instead of the pill. Just sort of poison your worker in case you're, for example, doing testing or you need to kill it abruptly. So how does this work? Well, the reap function is quite easy. It just takes a reaper and returns this reaper response, which is a sort of an either in disguise. And we are sort of leveraging on this pick tbq timeout function that we wrote, which is a variant on the STM original one, pick tbq. And basically, if we get a left out of this pick tbq timeout, it means we have been poisoned, so we die. If we get a right nothing, it means the timeout triggered, so this starvation time eventually triggered. And here we want to check the condition. If the condition is true, then we finally die. Otherwise, we sort of carry on. And the same is true for if we get a right of a just, which means that there is still more job to be done. And we carry on. And this is the peak tbq timeout that I told you. So if you concentrate on the equation at the bottom, where we have like a just timeout after, here I think is where really Haskell really shines. And this is we were able to leverage STM and the lovely instance for the alternative here defined to really write this concise and expressive code. So it basically just says we try to pick in the queue for a heartbeat. We just pick from the TBQ this heartbeat TBQ. If we do not have success, then we try until a timeout. If we still do not have success, we try and take from the flask. And if we did, then we have been poisoned. And this works well thanks to how the alternative definition is written there, which is written in terms of retry and or else. So I put the definition there just to refresh the audience. So or else will try the computation on the left. If that retries, the one on the right will be retried. If that retries as well, the computation as a whole will be retried. So it's a sort of flipper, which it just works and I think is really readable. So that was really a nice use of STM. And this is how the transcoder looks like. So we have one transcoder associated for each queue, and we have a queue roughly for each job size. So we are sort of able to have like a fine-grained control over the machine instance type we want to associate with a particular kind of job. It's essentially a state T in disguise with I/O at the bottom. And the way we apply it, we sort of wrap up the IMQP Haskell binding, which sort of force us to register this callback every time we pull another message from the other end of the socket. And this is why I needed this sort of mutable variable to sort of communicate back, because once you initialize this callback in your boot procedure, you do not have any sort of way of picking inside this callback. So this is why we are doing this. And the callback itself is pretty easy. So we sound the heartbeat and say, OK, we have some job to do. We do the transcoding stuff, and then we signal done. And we sort of wait for the next batch. And the new transcoder, so to create a new transcoder, you just need to provide this function, which eventually yields this I/O non-blocking action, which is nothing funky. I will sort of tell you in a minute. And we just return a transcoder of unit. And when we put this into production, I mean, it worked, which was great news. I mean, it didn't blow up, but it was sort of not very performant. I mean, the cost didn't change much. I mean, we were paying exactly as much as we was before. And the reason is because Amazon doesn't bill you for the fractional billing hours. So it means that if you spawn a machine at t equals 0 and you kill it at t equals 10, Amazon bills you for the entire 1 hour bill. So it means that you're just wasted 50 minutes of free time, essentially. So we needed to have a way of saying to the workers, even if you're starving, please stay there until the next billing hour. And at that point, only at that point, if you're still starving, then please die. And we leverage another feature of RabbitMQ, which are the consumer priorities. And instead of giving you the definition, I will just show you an image. So essentially, if Rabbit is in the position of delivering a message to two workers which are equally able to receive that, so that they are both available, it will pick the one with higher priority. So something really, really simple. And this this priority for us, it will be just 60 minus the uptime modulo 60, which means that if a machine just spawned, that figure will be quite high. It will be roughly 60. So we will have a high priority. As we are approaching the next billing hour, that will sort of almost decay to something really small. So the scaling, the priority will be really small, which has the effect of sort of self-excluding a machine from the cluster, because Rabbit is less and less inclined to deliver the message to that machine, so that machine will sort of evict themselves from the cluster directly, which is what we want essentially. And this is why we had to use this non-blocking action abstraction, nothing funky, but because in order to update the consumer priority, there is no way to do this dynamically once you spawn your consumers, at least in the MQP API. So the easiest way was simply to cancel the previous consumer once you did like a full round trip of transcoding and spawn a new one. So this non-blocking action is just a way of getting our hands on this consumer tag, which identifies a consumer, to be able to call cancel consumer on that tag. And that's just basically it. Putting everything together is quite a dense slide, but just concentrate on the pattern matching at in the middle. So if we have this, our transcoder type, it's a production transcoder type, we just sort of, our timeout will be set to 2 minutes. We check if we are close to the next billing hour, doing that computation I told you, and we read from AWS, which is using an API from AWS itself, which essentially kills the machine, sort of informing AWS, okay, this is not a failure, this is sort of, it's a suicide in a sense, so it will not try to replace the machine to compensate the loss in capacity, so it will be smart. If we are, for example, in development or in other environments, we do not want a tool to rip, or we perhaps want to spit some sort of funky message on the screen. So this is why we are doing the other implementation over there. And this is a bunch of screenshots to check the results, perhaps not very pretty in quality. Basically, this is Kronos aggregating stats from Pan, just to give you a glimpse of the other projects we have. And this was the cost, the EC2 cost, before we put this scaling algorithm at work. So this was using the naive algorithm. And as you can see, it was almost capping $150 per day. Once we put this into production, we basically shaved almost 50% of the cost. And we were not even capping $60 US. And this is how our scaling now works. So this plot over time the number of instances spawned. And as you can see, we sort of rapidly shrink up, and then we sort of rapidly goes down, and we keep cost at bay. So we can basically have 0 machines over weekends or overnight, and it doesn't cost us anything, which is really, really nice. OK, so what's the elephant in the room? Well, it's not as big as the one in the picture, but I'm trying to anticipate a question from the audience. And the question here is, why not use Cloud Haskell? Well, I will put just 3 sort of answers to that. Well, first of all, we started the project 2 years ago, and basically Cloud Haskell was not as mature as it is now. Secondly, peer discovery would have been really painful, because of course Cloud Haskell doesn't come with that out of the box. So we'll have to perhaps put something like the rough peer discovery part on top of your cluster, which will have complicated enormously the implementation. And last but not least, Cloud Haskell encourages Erlang-style actor-based communication. So nodes will needs to know each other in order to communicate, but we do not want that. We wanted to have our components to be stateless. That's all I had. Thank you. Projects. So they either talk to Atlas or they talk to, Hermes itself. But so they, in a sense, they talk to internet, but not in the sort of outside internet, in our sort of, but yeah. This is why we sort of choose this other technology, because there was like nobody was ever fired to choose EBM, so it was true for Ruby as well. So they picked this other sort of conservative choice on the front end, and we kept Haskell, but it was actually a success. So use it like bits of Erlang.
Okay. So in terms of structuring Erlang apps,
in the Erlang sense, we are not doing any of that. We are sort of, I wrote a small library, which I don't want to sort of make this a plug, but I wrote this library called Thread Supervisor, so which basically you can hook a supervisor, like an Erlang style supervisor, to your fork.io actions. And the supervisor will basically ensure that if your IO actions dies abruptly, it will be sort of restarted. And we are using that in a couple of places. So if you saw the callback I was talking about when we were doing the transcoding stuff, that fork.io in reality in production is using my library to make sure that if we die in the middle, we can restart the consumer. That's how close we get with the supervisor tree.
Is there any Haskell in your armband?
Okay, so this guy is a Mayo armband. So it's a funky device which basically maps your the signal from your muscles to commands for the computer. And the cool thing is that it comes with WebSockets API. So I actually wrote using Jasper, WebSockets Haskell library, a small program which just listen for the pause. So a pause is just when I was double tapping. And when detects that, is using the Apple script library, which is just a quasi-quoter on the Apple scripts, and it just use that to advance the slides. So yes, there is Haskell in my arm.
Thank you very much.
Thanks.
Haskell, no, not Haskell. Coffee and tea is downstairs.